So in this lesson, we will talk about denial of service attacks and defenses. We'll talk about what denial of service attacks are, various defenses. We'll talk about how to infer denial of service activity, and we'll talk about how to secure networks against denial of service attacks using software-defined networking. So what is denial of service? Denial of service is simply an attack that attempts to exhaust various resources. One resource that a denial of service attack might exhaust is network bandwidth. Another is TCP connections. For example, a host might have only a limited number of TCP connections that it can open to various clients. Or the denial of service attack might attempt to exhaust various server resources. For example, this victim might be a web server running complicated scripts to render web pages. And if the web server suddenly becomes the target of a bunch of bogus requests, the server could spend a lot of resources rendering pages for requests that are not legitimate. Before 2000, these denial of service attacks were typically single source. After 2000, with the rise of internet worms, as we saw in an earlier lesson, these attacks could become distributed, effectively being launched from many attackers. Let's talk about three different types of defenses against denial of service attacks. First, we have something called ingress filtering. Then we have something called URPF, or reverse path filtering checks. And then in the case of an attack on TCP connection resources, we can use something called TCP SYN cookies to defend against denial of service. Let's suppose that we have a stub autonomous system whose IP prefix was 204.69.207.0/24. Now, if this is a stub network that has no other networks connected to it, and this is the only IP address space that this network owns, then the router that is immediately upstream of that internet service provider can simply drop all traffic for which the source IP address is not in the IP address range of that particular network. So this is foolproof, and it works at the edges of the internet, where it's very easy to determine the IP address range that's owned by a downstream stub autonomous system. Unfortunately, it doesn't work well in the core, where a particular router might have a lot of difficulty determining whether packets from a particular source IP address could be allowed on a particular incoming interface. So the solution that operators try to use in the core is to use the routing tables to determine whether a packet could feasibly arrive on a particular incoming interface. So if a router had a routing table that said all packets for 10.0.1.0/24 should be sent via interface 1, and all packets destined for 10.0.18.0/24 should be sent via interface 2, then URPF says if we see a packet with a particular source IP address on an incoming interface that is different than where we would have sent the packet in the reverse direction, then we should go ahead and drop this packet. So the benefits of URPF is that it's automatic, but the drawbacks are that it requires symmetric routing. And we know from earlier lessons that routing in the internet is often asymmetric. Therefore, in any situation where asymmetric routing is a possibility, it is not possible or reasonable to use URPF. So we've talked about ingress filtering and URPF checks, and let's now talk about the use of SYN cookies to defend against TCP-based denial of service attacks. So in a typical TCP three-way handshake, the client sends a SYN packet to the server responds with the SYN ACK, and the client then returns with an ACK to the SYN ACK, at which point the connection is established. The problem in a typical TCP three-way handshake is that the client can send a SYN and cause the server to allocate a socket buffer for that TCP connection, but then if the client never returns, the client can force the server to allocate many socket buffers simply by sending a lot of SYNs and never returning. In fact, these could even be from spoofed IP addresses. So in other words, the client has absolutely no accountability and no obligation to return to send the final ACK, and yet can cause the server to allocate resources. This is a problem, and the solution to this is called SYN cookies. In the TCP SYN cookie approach, When the server receives a SYN from the client, the server, instead of allocating a socket buffer for the tuple associated with the connection, the server keeps no state and instead picks an initial sequence number for the connection that's a function of the client's IP address and port and the server's IP address and port, as well as a random nonce to prevent replay attacks. An honest client that returns can then reply with an acknowledgement with that sequence number in the packet. The server can check that sequence number simply by rehashing all of the information that it already has, thereby determining that the acknowledgement here corresponded to the previous SYN ACK that it had sent the client, without requiring the server to store any state. Only if this sequence number matches the one picked by the server in the SYN ACK does the server actually establish the connection. So as a quick quiz, what are some of the advantages of TCP SYN cookies? Is it that they can be applied to filter traffic in the network core? Is it that they can prevent the server from exhausting state by setting up socket buffers after receiving a TCP SYN? Or is it that they can defend against UDP flooding attacks? TCP SYN cookies can prevent a server from exhausting state after receiving the initial TCP SYN packet. Let's talk about how to infer denial of service activity using a technique called backscatter. The idea behind backscatter is that when an attacker spoofs a source IP address, say on a TCP SYN flood attack, that the replies to that initial TCP SYN from the victim will go to the location of the source IP address. These replies to forged attack messages are called backscatter. Now, the interesting thing about backscatter is that if we can assume that these source IP addresses are selected by the attacker at random, then we could set up a portion of the network where we could monitor this backscatter traffic, coming back as SYN ACK replies to forged source IP addresses. If we assume that these source IP addresses are picked uniformly at random, then the amount of traffic that we see as backscatter represents exactly a fraction that's proportional to the size of the overall attack. So for example, if we monitor n IP addresses and we see m attack packets, then we expect to see here n over 2 to the 32 of the total backscatter packets and hence of the total attack rate. If we want to compute the total attack rate, we simply invert this fraction. So for example, in this case, if our telescope were a /8 or 2 to the 24th IP addresses, we would simply multiply our observed attack rate, x, by 2 to the 32 divided by 2 to the 24th, or 255. As a quick quiz, let's suppose that our telescope is monitoring 2 to the 16th IP addresses. And let's suppose that in that telescope we see 100,000 packets per second. What's the total attack rate? Since we're monitoring 2 to the 16th of the entire internet, or 1 over 65,535 of the total internet, we simply need to take the rate that we've observed and invert that. In this case, that rate would be roughly 6.5 billion packets per second.